All right, welcome to Maxwell's Demon. This is a time where we find out about a famous, strange quirk of physics that has been debated by physicists for 100 years or so. And so this is Physics X, Extraordinary Concepts in Physics, coming to you from the beautiful downtown studios of Michigan Technological University. So here we're going to try to review some of the major topics of physics and just focus in on the concepts and try to use as little math as possible. Almost everything is available on Wikipedia. You can find out all the lectures, and there's now more than 25 on Starship Asterisk Physics X. And if you can read this, you don't need glasses, and you can just go there and find them. They're on iTunes as well. So we'll start off with one of the basics of Maxwell's Demon, which is what is entropy? Entropy is a word that doesn't usually come about in everyday life, so let's see if we can understand it because it's important to Maxwell and his demon. Is it the number of configurations an item can have? Is it the amount of disorder an item can have? The temperature an item can have? Or a new compact car by Chevrolet? The entropy. Actually, they name a lot of cars after physics. There's like quantum and stuff, and there's physics stuff. It's not uncommon for physics and astronomy to be the names of cars. Sadly, though, it's not that. It's the amount of disorder an item can have. And so physicists can try to accurately portray what that means. What does the amount of disorder mean? And so there are mathematical ways of coming to terms with that. Typically, one way to picture it, although it can get you in trouble, is that objects that have higher temperature typically have increased entropy. Not always. In general, temperature can vary across an item, so you can have a ball, and the left side of the ball could be hotter than the right side of the ball. Temperature really is a measure of how fast particles are moving, but a whole item should have one entropy that's measured for it. So here's the next question. Can the amount of disorder in an isolated item ever decrease over long periods of time? No, that would be against the second law of thermodynamics, something you might have heard about. Yes, sometimes order increases, sometimes it decreases. And are you saying that if I wait long enough, my room might clean itself? So actually, there's truth in them all, but the answer is no, that would be against the second law of thermodynamics and is even partially a statement of the second law of thermodynamics. So entropy is a statistical thing, and an isolated system can only become more random on the average over time, which increases entropy. Oops, let's cross that out. I was going to do that, So if you have a lot of states of something, so for instance, if you have a lot of pennies in a jar, I noticed when I was a kid, you could sit there and you can stack up all the pennies in the jar, and they can be all there, and they can be all on the bottom of the jar, and you spent time increasing the entropy. But if you were to shake that jar, you would then find the pennies would go in every which direction, and they would have their entropy would be increased. Now, what does that mean? So every place a penny could be can be considered a state. And you consider that all the states where they're all stacked up, they're rare compared to the number of states where pennies are in every which direction. So that entropy the pennies in every which direction can be considered to have higher entropy than all the pennies stacked up. Still, any one state, any one configuration where the pennies are in every direction is just as likely as any one state where the pennies are all stacked up. It's just that there's lots more states where they're in every direction. Got it? That's the guts of entropy, so far as I understand. So, which of these boxes has the higher entropy? Would it be the box on the left? So let's ignore the little demon here right now. He doesn't yet exist. So here we have a box on the left, and we have two kinds of particles. We have hot particles. Let's go to green here so I don't show bias. There's hot particles in red moving fast, and cold particles in blue moving slow. So does the box on the left have higher entropy, or does the box on the right here, where the cold particles are over here and the hot particles are over there? Or is it the two boxes in the center? So each of these is considered a box. This unit here is considered a box, and that unit here is considered a box. Each box is two compartments. So the answer is the box on the right has actually lower entropy. Did I get that backwards? All right. The box on the right has more order. I hope I didn't get that backwards. And the box on the left, so it would have a lower entropy. So if you were to shake these, if you were to remove these partitions, then you would get more something like this after some time than something like this. lots of states like this exist and not so many states like that exist. So there are fewer ways to arrange the hot and cold particles to get the box on the right than the box on the left. Okay, so now we get to Maxwell's demon. So a demon appears that can let particles pass between the two compartments of the box. What is the minimum amount of energy the demon must expend to open the door between the two box compartments? So here you see, let's go back previously, here are the two box compartments. Let's not consider this one. So there's a door here. What's the minimum amount of energy you need to open that door? Is it 0? Is it the kinetic energy of one of the cold particles? Is it the kinetic energy of one of the hot particles? Or is it about 1.5 Zorkels? Drum roll, please. It's 0. How can anything be 0? Well, as you know, my definition of 0 is something that's so small, it's smaller than every other thing in the problem, so it's effectively 0. A hair-triggered, smoothly sliding, well-oiled door with a spring to bounce it back into a closed position could be fashioned, for example. That would have just minuscule amount of energy needed to open and close it. So the amount of energy opening and closing the door isn't important. So this is one of my things when I was learning Maxwell's demon, thinking, oh, how come no one ever talks about opening and closing the door? So after thinking about it, this is what I believe to be the case. But it is not the end of the problem because the demon now chooses to let only fast particles from the left pass to the right and only slow particles from the right pass to the left. The demon does this only by opening and closing a small door at just the right times. Is the demon able to get all the slow particles on the left and all the fast particles on the right? Can the demon do this? Can the demon create a lower entropy situation? Yes. Good for him. That's one cool demon we have there. No, he can't do that. That would decrease entropy. Or I said maybe, and that's final. So, answer is yes, good for him. He can do it. It is clear the demon can decrease the entropy of the system, and he or she can do it using a door that requires almost no energy to open and close. Does this violate the second law of thermodynamics? Yes, which is good because I didn't like that law anyway. It was not my favorite. No, because somehow the demon is using energy, and with using energy, the demon is creating entropy. Or I'm not sure, but don't tell the demon because we need the energy. So that one is no, because somehow the demon is using energy and generating entropy. It is clear the second law will hold. No one has ever been able to build such a demon in practice. Somehow the entropy of the demon must be increasing. So what is it? What's going on? What does the demon do to increase his entropy? Is it sliding the door open and closed between compartments? Maybe my wording was so careful I missed something there. Maybe measuring the speed of the particles. Maybe that's what does it. Maybe thinking about when to open the door. That requires some minimal energy. I know human brain takes a lot of energy you need to eat in order to think. Maybe noting the speed, writing down the speeds of all the particles in some way. Has to be recorded in some way. Maybe that does it. Maybe erasing the speed of old particles. Maybe that's what does it. What is the demon doing to increase his energy and entropy? Well, probably got it wrong. Sorry. Please try again. We'll wait. Okay, here we go. Got it? It erases the speeds of the old particles. So who got that right? Not me for a long time. I had to read about it. Can he just use a really large USB drive to just write down all the particle positions? Then he won't have to erase. Well, it turns out that after some amount of time, any drive will fill up. At that point, the only way to tell which particle should be let through will involve recording information that is stored over old information. Therefore, some information must be erased. And erasing, oddly enough, seems to be the key to our current understanding of Maxwell's demon. Before I explain that more, let's take a history break. This was first created by James Clerk Maxwell Famous physicists created Maxwell's equations in the 60s and 1860s and 1870s. First, it appeared in a letter to a friend. So old-time physicists sent not email to each other, but lots of letters to each other. It was published in his book, Theory of Heat, in 1871. The term demon was coined by Lord Kelvin in 1874. Demon really meant mediating, not devilish, although people put devil. It's more fun to think of it as devilish, so I like that interpretation, even though it's not what was meant. It is still under debate. You can still find people debating this in journals, in fact, even today, by famous physicists. So, erasing information, it is thought, creates entropy. Think of erasing information as an irreversible process. So you write on a chalkboard, say. So the chalk need not go anywhere when you erase it, but you're increasing the entropy of the chalk when you erase it. You're mixing it up. It becomes more randomized. It's not a reversible process. So to erase something on a physical device has physical similarities to that. It turns out it must increase the entropy, so far as we understand. Erasing information on even the smallest device will result in an entropy increase, and the smallest bit of information is thought to be kT ln 2, natural log of 2. Okay? So recent analysis, including the energy the demon must use, and hence the entropy the demon must generate, these analysis still has controversial aspects, as I said. So that uneasy feeling you have about this, that you might have gotten wrong before, some physicists still have that feeling today. And it shows that even some very fundamental, very simple experiments get to the core of physics and is important for understanding physics to understand them. And full understanding of them comes sometimes slowly, hundreds of years, and small aspects of it are still being debated today. And with that, I'll ask you to keep Schrodinger away from your cat, and more fun next lecture.